Okay, this is live now from the Virtual Jug and from Devox London, Devox UK, so in London.
Yeah.
And this is a Virtual Jug session which we are actually presenting to a full room. Hey, everyone's live on the VJug now. Woo!
Wave.
There we go, wave, be happy. Okay, and joining us, this is I call this a virtual jug. Everyone is here but you, Lucas. Welcome to Lucas Edda. Where are you calling from, Lucas? In Switzerland or?
From Switzerland, yeah.
From Switzerland. Whereabouts in Switzerland? Zurich?
St. Gallen.
Say again?
St. Gallen. You don't know it. It's in the east.
No. So let's just say Zurich.
Yeah, Zurich.
and so, Lucas, who are you? You're the CEO of Data Geekery?
Yeah, that's correct. And Data Geekery is the company behind Juke, which many of you may know as the new Java way to interact with SQL.
Awesome. And what are you going to be talking about today?
So today's talk will be about SQL, of course, and the title is How Modern SQL Databases Come Up with Algorithms That You Would Have Never Dreamed Of.
Okay, it'd be interesting to hear what you think of modern what did you say? Modern SQL database, right?
Yes.
Excellent. I'm looking forward to the definition of that. So joining us as well is Roberto Cortez. Oh, look at that.
Hey. Hey, Lucas, how are you doing?
Hi there. Great. How are you?
I'm fine, thanks.
So Roberto is also one of the leaders of the Virtual Jug. Helps with the book club, and also leads the book club and also helps with VJug 24, which is very much appreciated. A little sneak. Shall we announce it? Yeah, let's announce it. Save the date for October 25th when we're going to be also doing our second edition of VJug 24, which is 24 hours of live Java conference, 24 back-to-back sessions. So that's going to be kind of fun. If anyone wants to ask questions, they can ask it in the room or online. We'll get IRC up online. You can also ask here within IRC if you really want to, but that's kind of a bit meta. And without further ado, let's pass over to you, Lucas, and we can start.
Will you read the questions to me?
Yeah, we can read the questions.
Okay, perfect.
You not read, Lucas?
No, I stopped reading, you know.
Oh, really? Okay.
So you can see my presentation?
You can.
Perfect. Is it all animated now?
It is.
Perfect. Okay,
and
so we can start.
Just to say, we have a hard stop at when? 6:05?
66608. No, exactly.
6. Because Roberto has got a an Ignite.
No, not blind Ignite.
Not
just
blind.
a plain
Ignite.
Ignite.
And I've got one straight after. So
at 6:05 or 6?
Yeah, 6:05.
All right.
6:05. Yeah. So
okay,
and to you.
So let's go. How modern SQL databases come up with algorithms that you would have never dreamed of. Or the short version of this title is SQL is awesome. Why are you all here? So I understand this is the Java user group, the virtual Java user group, or the Devox UK conference. So everything is about Java. So you're here because you think this cannot be true, right? This must not be true. And you will run out of this room. Is it true though? Or, oh my God, I'm going to rewrite all my code to SQL. Excellent. So me, I'm Lucas, the founder and CEO at Data Geekery, as Simon already told you. I work with Oracle and Java mostly, and I'm a Java user group board member in Switzerland. So if ever you want to come to Switzerland, do some vacation and talk at our Java user group, please join me. Or also at the Vox Day Zurich conference, which is also a part of the Vox franchise. And I believe that SQL is a device whose mystery is only exceeded by its power. Why do I talk about SQL to Java conferences? SQL is the only ever successful mainstream and general purpose first generation programming language. And it is awesome. So why doesn't anyone else talk about SQL? It's that awesome. I don't know. I have absolutely no idea. No one talks about SQL at Java conferences. Everything is microservices and stuff like that. No one talks about SQL, except maybe Vlad. Vlad is a very nice guy. He's the Hibernate developer advocate, and he started talking about SQL as well at conferences. So this is an example from Vlad's blog. It's a very interesting example because it shows the only important and only useful JPA feature, and that's that feature over there. So when you can write actual SQL with JPA, then actually you win with JPA as well. So who has seen my other talk? Usually I see hands in the room. Now I don't see any hands. Who has seen my other talk? I mean this talk here. This talk to convince you that SQL is awesome, right? If you have not seen my other talk, you should Google it. Just Google 10 SQL tricks, and you will find my talk all over the place. And my other talk is about these nice little SQL tricks like this one here. So here we have a recursive query for Postgres. And when we run this query, you've already mentally executed this query in your heads. Then you see immediately that is the result, right? So SQL is really a computation engine, or your database is a computation engine. Your application is sitting on a Ferrari-style computation engine, and you can run really, really awesome SQL statements with it. And that's the other talk. But today we're talking about more basic SQL, and it's still going to be awesome, right? So do you think this is SQL? Who in here thinks this is SQL? Anyone thinks here this is SQL. So if you think this is SQL, then this talk is going to be perfect for you. The other one was much more advanced. This one is very simple. So I've already talked about how SQL is awesome. This is the outline of my 2 talks. SQL is awesome. I've already shown this. So let's focus on how SQL makes you productive. And finally, we get to how SQL is fast. There are 2 ways of proving how SQL is productive. I could show you some examples, and I tried to, when I prepared this talk, I tried to find some examples which are really, really convincing and really, really nice examples of how really, really awesome SQL is. But then I thought about a second way of showing this is by showing the alternative. If you don't do SQL, if you do it in Java, then you see the alternative, right? So this is going to be a high-level conceptual story about SQL. We're not going into deeper levels of SQL today. For that, please watch the other talk. So business is asking, right? We're always doing stuff for business. This is the main purpose why we do stuff in programming. We do something for business. And this is our database, for instance. I'm just using this sample database, which is called the Sakila database. You can download it for free from Microsoft. And it has a DVD rental store. So what we have here is the film table. You see the film table in the middle. A nice little example database, film table, and we have actors here, and we have inventory, rental, and payment. So everything that we need when we rent DVDs. So business is asking, how much money did we earn with each film on each day, right? So that's a typical question that business will be asking us programmers, and we programmers will think, all right, I know how to solve this. Let's sit at the problem, and we're going to identify this is the film table, and this is the money. This is where the money is, right? So between film and money, we have to somehow join these 2 things. And we also have the day information. So we have all the information between these 2 tables. How much money did we make for each film on each day, right? So you see the path between these 2 tables? Excellent. So this is the path between these 2 tables. And now what we're doing is a join. Join these 2 tables between these on this path, and we don't have any problem at all. So right, we start, we write the query, and it's really, really easy. It's really easy. You see immediately that this is the film table, so we need money per film, right? So you see the film table right there, and that's the relationship between the film and the money. And now we aggregate per film and date, and then we have the result. Okay? Business is happy. This took us about 2 minutes to solve, and business is happy, and they can make a lot of money because they have many questions that we can answer. And now let's try doing this in classic Java. And by classic Java, I mean this, right? Okay, yeah. So I can't hear you laugh, so this is why I've introduced the laughing sound right here. So I kind of have the impression that you laugh at my jokes. So this is Java, and we're starting with a Java class. Everything starts with a class. You're still with me? Okay, perfect. So now when we add a class, obviously film is a tuple, so we can create a tuple in Java as well. We add some attributes. This is the only important information that we ever add in Java. It's these 2 columns. Now, because it's Java, we have to do it like this, right? This is Java. We have to write getters and setters everywhere because it's Java. No one asks questions about why we do this. We don't care. We just do it all the time, right? So someone really old from the 90s told us to do so. We're just not questioning it. Well, let's do it. And then we can't forget these, of course, as well. So we have to write hash code equals toString and all these things all the time for film, film inventory, for payment, for all of these entities. We have to write this code. And then, ladies and gentlemen, this is really dangerous code. So because it's Java, we add a factory, right? So we have to be sure that no one can actually instantiate a film without our consent. So we have to be sure that the film is instantiated with a factory, and the factory is also a dangerous place to work with because the factory cannot be instantiated by the user either. So we create a film factory builder. Exactly. And now this is still too dangerous in Java because we can't can't work with classes. We have to abstract these things, and we have to create interfaces instead of classes. And then we have private package private implementations that no one can see for these interfaces, right? And we're not done yet, because this is all too tedious. Now we've written so much boilerplate, we need to add some Spring to configure all of that, right? So we add some beans or some components. I actually got this wrong, so the real annotation would be component, and we need to cache some of these things. And then we add a little bit of Lombok, because obviously Lombok helps us be more productive. And then actually, while we're at it, we add some new libraries. We just found this new library, and then actually some more libraries, as you can see here, some more libraries. And in the meantime, the average enterprise Java bean that you've written right there is actually visible from space, right? You can see right there. That's the average enterprise Java bean that you can see from space. I've written it in St. Gallen, Switzerland, so that's where you see it. And if you want to have more information about this topic, here's a website for you to visit, Annotation Mania, because everything that we write today, tomorrow we'll refactor and write again as annotations. I think Roberto can actually show you more information about this. He has written some really nice annotations on his blog. So Roberto, be sure to show the audience about your annotation skill. Now, we're not done yet, right? We've only implemented the enterprise Java bean. What do we have to do? We have to actually get from the film to the inventory, to the store, to rental, to the payment, right? So remember all these joins, we have to do that as well in Java. Just because we're doing it in Java doesn't mean we don't have to do the work. So let's just start with the inventories. So we get a get inventories method here. So we get a list of inventories, and then we use this nice annotation. One more annotation can't hurt, right? So we write this nice little annotation, one-to-many. We're mapping the inventories by the film. So I'm sure you've seen these lovely things, right? Now, the question is, you want to discuss this or that? Right? Are you sure which one is the better? Again, ask Glad, the only other guy that ever talks about SQL at conferences. He has the answers, but we're not going to focus on these APIs. We're going to focus on the Java code. So this is the optimal result type that we want to have, right? We want to have how much money, that's right there, the money, the big decimal, how much money did we make per film and per date? So we're using a map of big decimal, right? Perfect. And actually, if you really want to go into the domain-specific, domain-driven design and everything, you want to model your domain not with a value, but with an actual money type. And we have a money type for this. There's the Java Money API, right? So the Java Money API is idiomatic Java, and you can see it immediately like there, right? Yes, idiomatic Java, Money API. Very simple way to interact with money in Java. Perfect. Okay. Right, so, but we're going to skip this part today. We're just going to think that big decimal is good enough for money. So this is the result type. Now let's think about, is this really a good result type? Or maybe this? Yes? You see the difference? Or maybe we should use this. What do you think is better? Maybe we want to actually show the result in a sorted order, right? So we have to use a tree map. And actually, the junior on our team, he said, okay, I know everything better. I'm going to write my own line. I will write my multi-key map, right? So because this is a map with 2 keys and 1 value, we actually need a new type for this that optimizes everything. And while we're still deciding for the correct collection type, everyone feels like this, right? So who in here in the room has felt like this before? You can ask, you can answer with your mobile phones, okay? So we've had the answer right now. Okay, so yes, the answer is yes. Okay, perfect. Now anyway, let's calculate for real. We've not calculated anything yet. We've just discussed data types, okay? So this is the result. Imagine the result is this, and now we're going to, we have to load all the films. Oh my God, and there's n+1 problems. We see it's really, really slow, but we'll optimize this later, right? And okay, we'll optimize this later. And urgent, this is really slow in production. Someone please optimize this. So typical Java development cycle, right? So now we loop over the films. And then we have to do something with each individual film, right? So what is this something? This something is we have to get another map from the map. So we have a map of local date and big decimal, right? So this is the same type. You immediately see this. Very, very easy. And oh my God, problem in Java, lazy initialization. This is null. At first, this is null. We have to initialize this first, right? Everyone agrees this has to be initialized first, because otherwise we get a null pointer exception. Oh my God, this is Java, right? Everyday Java work. You would know the feeling. Now, remember this discussion? Oh my God, nested map. Is it a linked hash? Same discussion again. But let's skip this discussion. Let's just assume we have lazy initialized the nested map. And now from this daily result, we go to the inventory. So from the films, we go to the inventory. And from the inventory, we go to the rentals. And from the rentals, we go to the payments. And now you really think about eager and lazy again. So eager was forbidden, but lazy is not much better either. So if you do this lazily, you get about 1 million queries, I guess. Right, so everyone knows? Okay, perfect. Now, because we don't want to have anything like eager or lazy in our code, we actually use the entity graph, right? The entity graph is what JPA came up with to actually run queries. This is the entity graph, ladies and gentlemen. So this is how JPA folks say for this particular case, when we go through the graph from film to inventories to rentals to payments, we're actually using only this named subgraph. And I'm feeling all like, oh my God. What is this going to do? Remember this slide here? I showed you the average enterprise Java bean. It's visible from space. Now, by the time you add all these annotations, the average Java enterprise Java bean is visible from Andromeda Galaxy, right? It's right there. You see from outer space, our aliens will see our Java beans. Perfect. Okay, anyway. Yeah, very fun. Okay, the looping is done, right? We're in the middle of the loop, so we put a value in this nested map. So the payment date and the amount is going to be put in the nested map. And oh my God, that's still not correct, because we still have to lazy initialize the 0 value. So we have to write this code here, right? So if the map contains the date, then we add it. Otherwise, we just put it, and all this code is getting so hairy. And someone says, okay, maybe Java 8 has something new. We can use compute. Compute is a much better method. So compute if absent, we can lazily initialize the hash map and lazily compute the value. That's much, much better, right? And everyone in the room is already feeling about themselves like this. Now, you see, everyone knows what's going to happen next, right? Now we figured out the algorithm completely. It's correct. And then this guy shows up. Business is asking again. Oh my God, did I say how much money per film? I meant how much money per film and store. Oh my God, all this work? Okay, so these are the programmer reactions. The SQL developer and the Java developer have different reactions, right? So this is the SQL developer. Whenever he has a change request, he's just, all right, I got you covered. All right, perfect. And this, ladies and gentlemen, this is the Java developer. This is the Java developer. Yeah, that's how we feel about change requests. Oh my God, everything changed again. Oh, back to the start. Okay, what does the SQL developer do? The SQL developer checks out his original SQL query, and then he just adds a little bit of white space right there. You see it, a little bit of white space, and then we add the store ID column right there, and we're done. Right, so business is asking, business got their answer again, and we got a paycheck and a raise and some more vacation because we're so good. Now the Java developer, all right, oh my God, this was my code with the compute, if absent, everything. Now I'm gonna do the cool trick as well as the SQL. I'm just gonna reserve some space right there, and then I'm going to add all of these things. Oh my God, who can see this? And now you see map of integer, of map of local date, big decimal. This inevitably triggers attention of the software architect. Software architect will say, that's this guy, by the way. He sees everything. He sees every one of your commits. He will say, we cannot have such type. We have to factor out this type in a new class. Right? You cannot have map of map of map. We have to have a class and a factory. So by the time you have this argument, you're just going to say, oh my God, I'm going to quit this job. While you and your architect engage in a nominal versus structural typing philosophies, and you prefer functional programming, and he prefers maybe object-oriented programming, there's this guy again. You know who that's coming next. You know this guy, right? Yes, exactly. The inevitable. Did I say daily revenue? I meant cumulative daily revenue. Oh, that's what I meant. Okay. It's the Java developers really, oh my God, what is cumulative daily revenue? What is a cumulative sum? So you check out the internet, right? So you go to the internet and you type in cumulative sum revenue. What does it mean? Okay. So you type the internet here and you get this result, and oh my God, what is this? Thanks God it's Friday. I'm not going to implement this. Meanwhile, the SQL developer, he's just going to add a little bit more white space at this nice little window function here. This is a window function which calculates conveniently the cumulative sum of the daily revenues over our payment tables. As you can see here in our database, the cumulative sum is just adding up the previous sum for each transaction. Wonderful. That is all we have to do in SQL. So I think you get the message right now. The difference that I've shown you is Java is a third-generation programming language. SQL is a fourth-generation programming language. This means in SQL, we only declare the result. We don't actually say anything to the database about how it should implement this algorithm. We just say, this is the result we want to have. Now figure the algorithm out for us. Wonderful, right? This is really wonderful. This is why the company is called Oracle, because we ask the Oracle a question and it will give us an expensive answer. So algorithms are boring. We really think algorithms are boring mostly. We don't care about these things. We don't care about writing algorithms. Using them is a different story, of course. We want to know exactly how to use the algorithm, but we don't want to write algorithms. We don't want to write a sort algorithm. We don't want to write data structures. We don't want to perform premature optimization. We don't want to think about, is linked hash map performing better than hash map? Is a linked list better than an array list? We don't want to think about these things. We don't want to think about data type details. When we have high-level business logic that we have to implement, if business is asking us some interesting question, we don't want to really think about, is it better to have a hash map of AB or a list of entries of AB, right? So in concept, in theory, these are more or less the same types, but from an algorithmic perspective, these data structures are completely different. And we have to decide all of these things all the time. We don't want to write local variables. When was the last time you actually enjoyed writing a local variable? Never, right? And caches. You thought about caches. We don't want to care about caches. Caches should be completely transparent. We don't want to actually store something somewhere. We just want this to work. We don't want to write loops and nested loops and nested loops. We don't want to lazy initialize anything or care about null pointer exception. Or you could discuss about optional. So optional might save you from the null pointer exception, but not from the lazy initialization problem. We do care about these things. We do care about business logic because that's our job. We have to implement business logic. And with SQL, we're just doing a bit of indexing, and then in most of the times, it's going to perform super well. So someone will tell you, okay, with Java 8, everything changes, okay? At least we can write functional logic right now. So this is a quote from Mario Fusco where he shows how we can do something imperatively or functionally with the stream API. So in the stream API, we see something very similar. We have something like from here, and then we have something like where right there. Then we have something like fetch next or limit in SQL, and something like group by, and this reads really nicely. So it's much easier to read when you put it like this. Of course, the example is really simple and really made for this example. But in a principle, SQL and stream APIs, they're very similar. They're very similar, so you can see the table in SQL is something like the stream of tuple in Java. So a tuple in Java, it's just a class. It's a class has attributes. Tuple in SQL is also attributes. And a stream and the table is exactly the same thing, more or less. A select operation is like map. Map gets a tuple as an input and gets a tuple as an output. Just like select, when you have a select expression, you have select first name, last name, you get a tuple, you produce a new tuple. It works in a very similar way. At least the mindset of doing these things is very, very similar. Distinct is the same thing as, of course, join and flap map are kind of similar. Where, having, and filter is the same thing. Group by and collect is more or less the same thing. Order by and sort is just a different name. Union all and concat, just a different name. Now let's look at our Java algorithm. This was the Java algorithm in an imperative way. Now let's write something really, really nice with streams. So we're just streaming and flap mapping, right? So this is essentially what we have to do. We stream all the films first. We stream all the films. Then we stream the inventories from the films. Then we stream the rental from the inventories. And then we stream the payments from the rentals. That's it. But now we have to access F and I in the collector. When we want to aggregate how much money do we earn on each day, we have to actually remember all of these types. We don't remember them with flat maps, so we have to nest them somehow. So here I'm using something like an entry, like a map entry, where I keep remembering the inventory, the film, the rentals, and the payments. Okay, so you can use some wrapper and pray for stack allocation to happen, right? So performance in this case is not validated yet. But okay, let's assume that this works. And now we just have to collect and just do some grouping, right? Easy. Everyone agrees this is easy? Perfect. Oh my God, all of these. So we have to remember this was the film, inventory, rental, payment, nested type, and we have to get the key to get to the film, back to film. And you don't see the types anymore right here. So, but it still looks declarative. right? So this is more or less the Java solution to doing the same thing like in SQL with Java 8. It looks declarative, and if you want to go one step further, I can do some little advertising here for the open source Julambda library that we're publishing. Julambda's goal is to bring a little bit more SQL to the Java language, so you can do something like this. You can do multiple aggregation and stuff like that. I'm going to show how we can improve the Stream API usage with Julambda. So instead of streaming, we will just use the Julambda sequence. So everything is sequential, not parallel. That's the difference in Julambda and streams. So what we can do now here, instead of having these nested types, we can actually just cross-apply. Cross-apply is a feature from the SQL language. It's available in SQL Server, Oracle, and Postgres, so we can cross-apply. It's a bit easier, so we can remember this cross-applies means we get the film and inventory in one tuple, and this automatically nests film inventory and rental tuple, etc. So I'll leave it up to you to read what cross-apply really does, but it makes it a little bit easier right here. So we can now have a film inventory rental payment object right there. Still, we have to dereference everything and again and again. So this is really a bit tedious. So we can maybe refactor because we didn't really need the rentals. We never needed the rentals except for joining, so we can factor them out. So right now we have it a little bit better. Just one entity has gone, and maybe we can actually use this group by operation. So this actually looks quite neat, and the result type is now also a little bit nicer. And okay, the point I'm trying to make here is how much time do we spend on this problem now? I already have to almost quit the show right now because Roberto is up next. So I have to stop right here. The point I'm trying to say here is you're already falling asleep with the Java solution, right? We can discuss this endlessly when the SQL solution was so easy. This was such an easy solution, and we could change it so easily as well. SQL is a fourth-generation programming language. This means it's a great improvement of developer productivity. We can write SQL so much faster because we don't have to worry about all these algorithmics and data structure details that we don't really care about. How much time did I spend talking about SQL so far? Almost nothing. How much time did I spend talking about Java? So much time. So SQL is easier. This also means SQL is more productive. So I think I've proven this second point. SQL is more productive. We're ready for change requests. So we're now reaching the final chapter, which is the best chapter, the one about performance. It's not only about making you more performant, but also the database itself. So how does SQL work? We have to understand first how SQL works. Now let's hear this guy again. How many films did each actor whose last name starts with A play in? This is a typical query, typical, maybe a bit academic, but let's run it. So the query will give this result in our database. So all these people have a last name that starts with A, and these are the number of films they played in. Right, so this is the query we want to run, and that was the query actually in SQL. So we'll select first name, last name from actor, film actor, joined, and then we check the last name starts with a group by first name, last name, and then we count. That is the SQL query. And now let's see what really happens. This is the syntax. We have to understand the syntax is not exactly the same thing as what happens logically. So people often criticize SQL because they don't like the syntax, and that's correct. The SQL syntax is a bit weird. It's really an old type of language, so you have to get used to it. But once you get a hang of the following slides that I'm showing to you, it's going to be much easier because the logical operations order is not the same as the SQL syntax operations order. The select clause is not the first thing that happens logically in your SQL statement. And observe, I'm saying logically and not actual order. The actual order, we get to that, is going to be displayed by the execution plan. So the optimizer will figure out the actual operations order. But now let's focus on the logical operations order. So the first operation is we're selecting the actor table and the film actor table. We're loading all the data from these two tables and join these two. So the join keyword is actually not a keyword from the select statement. It's an operator between two tables, right? So the keyword is from. From is the keyword that we execute first in the select statement. And now the second operation is the predicates. We apply the predicates in the where clause. So from produces tuples or records, and where reduces that resulted again, because we only want to have actors whose last name starts with the letter A. And their films. Now we collect groups. Group by is the third operation in this example. So we're grouping everything by first name and last name. That is the third step. And the fourth step, logically, is aggregation. After grouping, we aggregate. Now again, this is the logical operations order. It might well be that the database will do both steps in one go, or maybe even do something with a pre-calculated count value from an index or from a materialized view, but we don't care about that. Logically, it's the fourth step. after grouping. And you see 2 times we're using the count expression. Count star is in the select clause and in the order by clause, but the database may well choose to optimize these 2 expressions. It should actually, and execute them both in one step. So you can reference count star many, many times, and you don't have any performance impact. Now, count star is already calculated in step 4 before we project. So before we actually run the select statement, count is already there, and it's calculated. So now we project and we create this new tuple, and then we order by this pre-calculated count expression. This is the logical operations order. Here's a slide with pretty much the full logical operations order with all the clauses that you use every day. So from happens first, then where, and then some obscure connect by an oracle, if you're using oracle, group by, and then all the aggregations. And once you have calculated the aggregations, if you're using having, that happens now. And then window functions, if you're using those, let's skip model in Oracle. And then finally, now you're doing select, number 9. I use the laser pointer so you can follow my train of thoughts. After select, we apply distinct. And then we do apply union, intersect, and except. Then order by, only after this has been done. Then offset and limit. And finally, for update, if you want to do pessimistic blocking. So this is the logical operations order. And this explains a couple of things. For instance, aggregations happen here, right? Aggregate functions happen after group by and after where. This means this is the reason why you can't use aggregate functions in the where clause, because the where clause has already been executed. You cannot use an aggregate function in the where clause because they are calculated after the where clause. Or if you're using window functions, they're defined here. You cannot use window functions in the where clause either, right? Because they happen afterwards. But you can use window functions in the select clause, because the select clause happens after the window step. Now, column aliases, if you use column aliases, right? If you want to rename a column in your select clause, you can only use that in subsequent operations like order by. You cannot use an alias in where. This is quite tedious because we have to often repeat ourselves in the SQL language. It's an old language, remember, so it's sometimes a bit tedious to use. This explains why you cannot use a column alias in the where clause or in the group by clause, even if that would be really, really useful. So that explains a thing or two, right? Okay, but I told you that's not really what happens. Any algorithm that produces the exact same result as this logical operations order is acceptable. And we can see the algorithm from the database. For instance, this is the algorithm in Oracle. I'm going to show other examples afterwards. This is called an execution plan. So who in here has seen an execution plan in the past? You can use your mobile phones again to vote. Okay, so the result. Oh, okay.
Couple of people.
Okay, it's great. So great, I'm here. I'm showing you something new. I'm just assuming, right? I'm just making this up, but I'm assuming you've seen this. So just try clicking on these buttons here in Oracle SQL Developer or Postgres pgadmin or SQL Workbench for MySQL or SQL Server Management Studio. You have these buttons to display estimated execution plans and sometimes even actual execution plans. So there's an estimate and there's a real execution plan. That's a nice difference to know about. But in any case, the interesting thing here is, for instance, in the Oracle execution plan, we have how many rows are produced by each operation, right? So you can see right here, this join operation produces 154 rows, estimated 154 rows, and this where clause, the where clause where you select the last name starting with the letter A, it produces 6 rows. And altogether, more or less 13 rows. And here we have quite a big number. We're going to look at this afterwards, what this means. So you see the number of rows the database thinks it will produce with each operation. And here's the cost. The cost in Oracle is a bit weird, but in other databases, it corresponds to more or less the time it will take, probably. The database estimates how much time and how much resources will I need to calculate this result. So the actual execution order is always in execution plans, it starts from the bottom and goes up. So the first operation in the database is to get the row IDs from an index given the predicate. So I think pretty much everyone in the room would have thought that it is probably better to run the predicate first on the index and only then execute the join, right? So the join, even if it's logically first operation, it's not the first operation that gets really executed. The first operation is accessing the index, and then we access the remaining rows from the same table. Right? So that's the first thing that we do. The active table is loaded first, but only those rows that we actually need with an index access. And the third step is we're loading the entire foreign key relationship index into memory. Wow, that's surprising. If you look at this, the relationship index is being loaded into memory because the database thinks that's the fastest way to actually run this query. Right? We're not going to actually look up each individual actor and select their films. And then only when we've done these two steps, when we've loaded both tables, then we put them in a hash map and join them, and then we put another hash map to group the rows, and finally we sort the result because that's what we're required. Now the question is, we have chosen the same algorithm. Apparently, it's faster in this case to load 5,462 rows into memory than seeking 6 counts individually. So the database thought this was going to be the faster algorithm. And I think pretty much everyone in the room would not have chosen this algorithm. You would have chosen to select the 6 actors and then loop over these 6 actors and select all their films individually and count them. Now the difference is a hash join in algorithmic complexity notation, in big O notation, is O of n. So it's linear. You can execute a hash join in linear time with n being the number of film actors. So the bigger table is the one that influences this algorithm. Whereas the nested loop join with indexes, it might have a worse complexity right here. So maybe it's log m times log n, or maybe it's even worse, m log n. So we have a worse complexity. For small amounts of data, this might be better, but for large amounts of data, the other one is better. So which one is better all the time? It depends. So see, the database, it always considers these algorithmic complexities. So this might be the data that you have, or what you think you have. So maybe we have here a couple of algorithmic complexities. Sorry, I'm screwing up my PowerPoint. So here, linear time, logarithmic is the green curve, linear is this one, and this one is sorting, n log n, etc. But maybe what you really have, your data set, is the small size here. Right? Maybe you have this data set where all the complexities are kind of inversed, where the worst complexities might perform better than the better complexities. So linear is not always better. Maybe quadratic is better for small amounts of data. And the problem is also, quadratic is also better for your machine. When you work as a developer with developer data sets, then you are always in this area where everything seems to be super fast, and in production you have a lot more data. So you really should think about algorithmic complexities and understand these. Here's a nice link to learn about these things if you've never seen it, or if you want to refresh your knowledge about algorithmic complexities and time and space complexity. Here's another thing. Let's talk about histograms. Databases do this. This is a histogram. We have here the bank account transaction table, and this is the distribution of our amounts. So pretty much in all bank accounts, we have probably something in the middle, a bell curve, where we have all the time, we have something like we pay for the restaurant, or we are the restaurant and we get the money, or here at the end you see we buy a new car, or we are the car seller and we sell a car. So we have a lot of transactions here in the middle, and only few transactions at the end, at the other edge. Now imagine we have these queries, these two predicates. Someone wants to check if the amount is between -2,000 and 2,000. Someone else wants to check if the amount is between 5,000 and 9,000. Both of these ranges are the same size, right? But do both predicates profit from indexing? This predicate here is not selective at all. We're selecting almost all the data. So when you have an index on the amount column, we're not profiting from using the index. Whereas here, we can certainly use the index. See, these two predicates are two very distinct predicates depending on what data we're selecting. So accessing the index is only worth the pain if it helps reduce the result set. Otherwise, just read from the table. When we read from the table, we just load it into memory completely, or we scan it completely, and the database knows all these things. This is nice stuff. We never have to think about these things until they go wrong, and they don't go wrong very often. Right? So the database can always choose the right execution plan depending on what you're doing with your queries. And your queries may change in production. Maybe you have a lot more data tomorrow than today, and your database can adapt their execution plans. So how many rows are returned from a table? The database knows this. How many rows are returned from a query? It knows this. How much does it cost to access to this? The cache. How often is this query run? How often is the table accessed? How much memory do we have? I'm deliberately skipping these things because we don't care about these things, right? How many processes are running in parallel right now? How does the query perform with this bind variable? Are we running on HDD, SSD, flash, or RAM? Oh my God. Right? So in-memory NoSQL DB vendors that try to tell you we have to do everything in RAM now, but maybe you want to offload something to the disk. RDBMS can optimize all of these things, and everything has a cost. So how does SQL work? Everything has a cost. So a parse SQL string produces an expression tree, and I'm going to go through this really fast. I only have 4 minutes, 9 minutes, right? 9 minutes. Okay, so this is a parsed SQL string. Let's imagine this is a parsed SQL string. This is an expression tree. So we can say A plus A minus B is an expression tree. And we can say multiple expression trees are equivalent, so they can be transformed into each other. So we can say A plus A minus B is exactly the same thing. By the laws of associativity of addition, we can also say A plus A minus B, and we get the same result. It's a different expression tree, but we can easily see it's exactly the same thing. Now that we have shown this, we can also do another transformation. We can actually say this is also the same thing, right? 2 times A plus minus B is also the same thing. And this is a much better execution plan if accessing A is super expensive. Imagine A is on the disk and B is in memory. Do you want to run the first execution plan or the second one? So this one is obviously much better. So the database does all these things. It transforms your query into other queries. Each expression tree has a corresponding execution plan and an associated estimated cost. And then the best plan that the database can come up with, the one with the lowest cost, is chosen. And then, at least commercial databases do this, the actual execution cost is compared with the estimate. So the database can only estimate, and then it runs it, and it gets actual costs, and it can use this information to improve future estimates and future executions. So when is the last time you wrote Java code that did this? When is the last time you wrote Java code that can adapt its own execution in runtime, depending on the data set that you're transforming? Your estimates aren't even done in production. You're estimating stuff with your developer data set. Okay, so the production is here, your estimate is being done here, and you see immediately why SQL is fast. SQL is super fast because it can adapt its execution plans and its algorithms in production. And now that you know all of this, which one do you prefer? Do you prefer this, which was already much, much more tedious to write, or this, which is going to be much faster anyway, right? And I'm telling you a trick. So I'll lie to you. It's not always easy and simple to tune SQL. But imagine tuning something that was written in Java, which has the equivalent complexity. It's going to be even much harder. So here's a nice quote from Raphael Winterhalter, which he recently published. He's the developer of ByteBuddy, fellow Java champion. And he says, knowing Java performance fairly well is a nice trait, but not knowing my database well enough still punches me in the face once a week. Right? So most of the time when you have performance problems, it's in the database, even if the database does the stuff already so good. So you have to imagine if you have to do all of this work that is already hard to do instead of in the database in Java, that would be just horrible. Okay, so why do I talk about SQL? SQL is the only ever successful mainstream and general purpose fourth generation programming language. So everything I did here is declarative. You can do everything in SQL declaratively, and it works extremely nicely. No one else seems to talk about SQL at Java conferences. I have absolutely no idea why, because it's such a great tool. It's 40 years old or even older, and it still works very nicely. It works much better than ever before because optimizers are really, really good today. They do all of these things and tons of other things. Now, everyone in the room asked, can I write SQL in Java? That's the big question, because you're writing Java most of the time. So yes, there's an answer from me. You can write SQL in Java using Juke, for instance, right? So Juke allows you finally to write type-safe SQL in Java. A little advertisement here. So every object in Juke is a table or a column in SQL, and then you have a type-safe SQL API that type checks your SQL state, and you get type-safe result sets back. And the way you feel about it, you will feel about writing SQL in Java as well. This is how you feel, or this. Okay, so you're convinced. Perfect. So what's the key takeaway in the from this talk? Can you do it in the database? Right? Yes, you can. Because SQL is Turing complete. That's part of the other talk that you should definitely look up. Look up on Google SQL tricks, 10 SQL tricks. You will see SQL Turing completeness. This means you can write anything in SQL. Perfect. Can you do it in the database? Yes. After you watch the other talk, you will see all the tricks. You know everything about SQL. And if you don't feel comfortable enough with the other talk, you can visit my 2-day SQL training where I explain everything very slowly from both talks, so you get a nice deep dive into the SQL language. Can you do it in your database? Yes. Most of these features that I display in these talks is SQL standard, so you can do all sorts of calculations, like the recursive query that we've seen to calculate the Mandelbrot set is a SQL standard query. You can easily calculate that in any database, unless you're using MySQL. MySQL is quite behind all the others, although MySQL 8 will catch up and implement window functions to calculate running totals as well, and recursive SQL as well. So MySQL 8 is quite promising. Looking forward to that. Should you use it? Should you do it in the database? Of course, you should do it in the database. Yes, absolutely. The database is the perfect place to put business logic because we've seen SQL is a logic programming language. It's a declarative programming language, and it's one of the best languages to implement such business logic. Right? So we've seen we're super productive. Do long titles or from a talk, attract attention. This title is super long, it's incredibly long, and still you have all the attention, you had high expectations, they were fulfilled. So yes, this also works. Will this talk ever end? Also yes, thank you very much. Google 10 SQL tricks and find the other talks transcript. You will love it as well. Thank you very much.
So we have this one. Yeah. Can you any questions for the room? Any questions from Sion, Vijay?
Well, I think we have a comment here. So this is coming from Carton's wage or something. Well, so if you assume that we all agree with you,
yeah, I assume that.
Are you yeah, of course. Are you suggesting that we just query the DB directly, or how is this integrated into the standard web CRUD app?
So the question is, should we write to the DB directly with SQL? Is that the question instead of JPA?
Yeah,
or what is
the question is just, should you just query the DB directly, and how do you integrate these with the standard web CRUD app? So basically, people are talking here about those dashboards that business loves so much.
Instead of CRUD. Okay,
yeah.
I told you only half of the story, right? I told you to also listen to Vlad, the other SQL guy that talks at Java conferences. So there are two topics on SQL. One is writing, and the other one is reading. I only talked to you about reading today, right? So reading is really the domain of the SQL language. When it comes to writing, when you write to the database, there are two types of writing. There's ETL jobs and data load jobs and these kind of things, batch jobs, where you still use SQL. And if you write CRUD applications, you're probably better off using some ORM or Active Record or something else that helps you write that SQL, because you don't want to write insert, select, update, delete all the time, right? So there's two parts of the story. There's the best parts of both worlds. Today I talked to you about SQL, and I definitely think you should write SQL directly, but writing is a different story.
Okay.
Yeah.
And that one's pretty much the same, isn't it?
Yeah.
Any other questions in the room? Anyone thought of any questions? No. Okay, so Lucas, thank you very, very much for your session. Awesome session as normal. And I do believe your other session, the 10 tips and tricks, is actually in the video as well. So feel free to go to either. And thank you very much. On Twitter, you are just Lucas Edder, right? L-U-K. Oh, there it is.
Right there.
L-U-K-S Edder. So feel free to ping Lucas with any other questions online.
Thank you very much.
Yeah, thank you very much. Cheers, Lucas.
Thank you, guys.
Thanks, everyone here.